Hey everyone, today we're going to talk about the invisible chemistry that's literally all around us. It's what makes lemon sour, what makes soap feel kind of slippery, and it's even happening inside your stomach right this second. Yep, we are diving deep into the world of acids and bases. Oh, we've all been there, right? That really uncomfortable, burning feeling after a huge meal. So you go to the cabinet to find something to help. But what do you grab? Lemon juice, vinegar, a little bit of baking soda mixed with water? Well, the right answer actually lies in some really cool fundamental chemistry, and that is exactly what we are going to unpack today. So, how did we even figure this stuff out in the first place? Long before there were fancy labs, people identified acids and bases using the most obvious tools they had, their senses. Let's start right there with the basics. Okay, so at their core, acids and bases are total chemical opposites. Think about it. Acids, like what you find in a lemon, taste sour. Bases, on the other hand, taste bitter. Now, since tasting random chemicals is obviously a terrible, terrible idea, chemists came up with a clever trick called litmus paper. An acid turns blue litmus paper red, and a base turns red litmus paper blue. It's a super simple visual way to see their opposing nature in action.
This brings up a really important point. If we can't, and shouldn't, taste everything, how do we safely figure out if something's an acid or a base? Well, for that, we bring in the chemical detectives.
These detectives are called indicators, and an indicator is pretty much any substance that gives us a clear signal, usually by changing color, when an acid or a base is around. We already talked about litmus, but even the turmeric in your spice rack is a natural indicator. Ever notice how a curry stain on your shirt turns kind of reddish when you scrub it with soap? That's chemistry. It's because soap is a base. This table is basically a secret decoder ring for chemists. It shows how different indicators react. Take phenolphthalein, for example. If you put it in an acid, it's totally colorless. Nothing. But add just a drop to a base and bam! It turns this brilliant, vibrant pink. Each one gives us a different clue to solve the mystery of what we're looking at. And get this, it's not just about what you can see. Some indicators actually work by smell. Check this out. If you take a piece of cloth that really smells like onions and add a few drops of acid, the smell doesn't change. But if you add a few drops of a base, the onion smell completely disappears. It's gone. In this case, your nose is the chemical detector. All right, so we know how to identify acids and bases. But now, for the really fun part. What happens when they actually react with other things? Let's see them in action. This is such a classic experiment. You take a little piece of metal, like zinc, and just drop it into some acid. Right away, you see these bubbles start fizzing up. That's hydrogen gas being created. And here's the coolest part. If you bring a lighted splint near that gas, you get this really satisfying little pop sound. That pop is the telltale sign of hydrogen gas. So here's the rule you gotta remember from that. Whenever an acid reacts with a metal, you are always gonna get two things. First, you get that hydrogen gas, the stuff that makes the pop. And second, you get a compound called a salt. It's a really predictable and fundamental chemical reaction. Okay, but what if the acid reacts with something like baking soda or chalk? Those are called metal carbonates. Well, in that case, you still get a salt and water, but instead of hydrogen, you get carbon dioxide gas. And this is where the fizz comes from. It's the exact same reaction that makes bath bombs fizz up or makes those volcano science experiments erupt. And here it is, the answer to our very first question. When you mix an acid and a base together, they perform a reaction called neutralization. They literally cancel each other out. And what are you left with? A neutral salt and just plain old water. This is exactly why an antacid, which is a base, helps soothe stomach acidity. It just neutralizes it. Okay, pop quiz. Let's apply what we just learned. Based on that rule we talked about, acids and metals, think about this for a second. Why is it a really bad idea to store something sour, like curd or yogurt, in a pot made out of copper or brass? You got it right. Curd has lactic acid in it. And since we know acids react with metals, the acid in the curd would start to react with the copper or brass pot. That reaction can create some new compounds that you definitely don't want to be eating. It's a perfect real-world example of chemistry happening right in your kitchen. So we've seen that all acids seem to react in pretty similar ways. But what's the deep secret? What is the one thing that actually makes an acid an acid? Well, turns out the answer is hiding in water. So check out this setup. You've got a solution of acid and water, and when you put electrodes in it, the light bulb glows. That means electricity is flowing through it. But here's the kicker. If you try the same thing with sugar water or alcohol, nothing happens. the bulb stays dark. So what's so special about acids in water that lets some conduct electricity? The secret is ions. When an acid dissolves in water, it breaks apart and releases positively charged hydrogen ions. We call them H+ ions. These little free-floating charged particles act like a superhighway for electricity, letting the current flow and light up the bulb. That's the real definition of an acid, anything that produces H+ ions in water. And you can probably guess bases do the same thing, but they release negatively charged hydroxide, or OH- ions.
Okay, now for a super important piece of lab safety that's directly connected to all this. The number one rule when you're diluting a concentrated acid is to always add the acid to the water, very slowly. Never, ever pour water into the acid. Why do you think that rule is so critical?
Well, the process of dissolving a strong acid in water is extremely exothermic. That's a fancy word for it releases a massive amount of heat. So if you pour a little bit of water into a lot of acid, that heat can instantly boil the water, causing the concentrated acid to splash violently right out of the container. By adding the acid to the much larger volume of water, the heat can spread out safely. That warning sign on the bottle isn't just a suggestion, it's a reminder of some seriously powerful chemistry. So we know what acids and bases are, and we know their secret is all about ions in water. Now, let's talk about how we measure their strength and why it matters so much in our everyday lives. This is the famous pH scale. Just think of it like a ruler for acidity that goes from 0 to 14. A pH of 7, smack in the middle, is perfectly neutral, like pure water. Anything below 7 is acidic, and the lower the number, the stronger the acid. And anything above 7 is considered basic or alkaline. And trust me, this scale is absolutely everywhere. The acid in your stomach is around a pH of 2, which is incredibly acidic. Tooth decay actually starts when the pH in your mouth drops below 5.5, because that's when acid starts to dissolve your tooth enamel. This little number has huge consequences for our health and for the environment around us. And you know, nature is basically the world's best chemist. That sharp, tangy taste in vinegar, that's acetic acid. The sourness of an orange, that's citric acid. Even that painful little sting you get from an ant, that's a tiny injection of methanoic acid. We are constantly surrounded by these natural chemicals. So let's end with this really fascinating bit of natural chemistry. The stinging nettle plant injects acid into your skin when you touch it. But really often, growing right nearby, you can find something called a dock plant. The sap from the dock plant is basic, and if you rub it on the sting, it neutralizes the acid and makes the pain go away. It is a perfect living example of neutralization. It just makes you wonder, what other incredible secrets of chemistry is nature hiding right there in plain sight?